Greetings again. For those who don't know me, my name is Dr. Sebukhudi, and we'll be continuing with our lessons. Today we'll be focusing on continuity. What do we mean when we talk about continuous functions? We're not going to be doing limits, but yeah, remember we started first with the intuitive definition of a limit, just playing around what do I mean by limit. That's when we use tables, then we use the limit laws. Then the previous lesson, we did the definite definition of a limit when you had to use those epsilon delta definitions. So today, actually, we get to talk about continuity. Remember the time when we did limits, we always said we want x gets close to a, but we don't really care what happens when x is equals to a. So this lesson is like actually what happens when x is equals to a. So that's what we talk about continuity. And please know that actually some of these lessons that we're doing here, they may seem obvious, but trust me, there's a whole lot of concepts that are based on this. For example, when we get to do differentiability, when do you know that a function is differentiable? When do you know that a function is integratable? Things like that. So such functions or such concepts, they get to be built on top of continuity, on top of limits. So basically, if you don't understand these small concepts that you're dealing with, it can be a bit tricky to understand the some of the concepts that you guys will be taught earlier. And actually in today's class, because I thought, you know what, yes, it's true that some of these lessons we have been focusing on just understanding. So some of the functions that we've been picking as just those functions that just for understanding's sake, for just for you to get the concept. But actually today, there's some examples that I get to show you actually the kind of functions you can expect here in university. Yeah. And today actually, I'm in the lecture venue, just to give you a feel of actually what's happening around here. So I think maybe you can just jump into the class already so that we can start with our class. So again, I'm going to turn off the video because I don't think you guys need to see my beautiful face, so that we can focus here. All right, let's shoot. Okay, like I said, we'll be focusing on continuity. So let's start first defining what is continuity. Remember that all those sessions when we're talking about limit, we're talking about x approaching a, but we said we don't care about when x is equals to a. And actually, I think with the time when we did limit laws on the second lesson, we are focusing on actually, we spoke about polynomials and we're talking about direct substitution, that some functions, instead of evaluating the limits, you can just do a direct substitution. And we said functions like polynomials and your rational functions, you can, as long as the function is defined, you can do a direct substitution. But actually there is a powerful tool, or actually that is based on a certain concept called continuity, of which it is what we're focusing on today. Such functions, actually the ones that you can do a direct substitution, are said to be continuous function, or actually they are continuous at that point. So because in the case we're talking about direct substitution at a, so it means actually those functions are functions that are continuous at a. So basically, let's get to define, or what do we mean when we say a function is continuous at a. So basically, this is the definition. A function is continuous at a if the limit as x approaches a of f of x is equals to f of a. And I know this definition seems very short, but trust me, there's a whole lot of information that is hidden behind this definition. First of all, let's the implication of this theorem. Let's go through them. First of all, it means f of a should be defined. When you say f of a should be defined, it means actually there should not be any asymptote, or the function should not have that that open dot when x is equals to a. That's number a. That's number one. Number two, it means actually the limit should exist. When you say the limit exists, remember that we're talking about the limit from the left and limit from the right should be the same, right? When x approaching a. And the third point that is very, very important, the limit exists, meaning the limit at that point should be the same as f of a at that point. So it means actually basically at a, you should not have an open dot, and it should be a closed dot, and that dot should be the same as the limit coming from the left and the limit coming from the right. Basically, I'm talking about graphical. This is what I mean. You can see that at a, we have this dot here. It means actually the corresponding y at a is actually that a. And again, you can see that the limit, the graph as x is approaching a from the left and from the right, both the function is approaching this f of a. So basically, that's what we can read from that definition. And again, it is not always the case, or not all functions are continuous. But again, when the function is, or if any of these properties, any of these three properties, if any of them is not satisfied, then we say the function is discontinuous. I hope I'm not too fast. So all these three properties, they need to be met for you to say that a function is continuous at that point. And if any of them is not satisfied, then we say that the function is discontinuous at that point, or we say the function has a discontinuity at that point. Let's look at this function here. So we want to look at this example of discontinuity when x is 1, when x is 3, and x is 5. Let's look at when x is 1. First of all, when x is 1, yes, the limit from the left and the limit from the right, they are there, and they equals to corresponding whatever y value. But again, we have an open dot here. So at 1, we do not have the corresponding f of a, or the limit is not the same thing as the f of a. So because now 1 is, the function is not defined at 1, then the function is not continuous. The limit exists, but the function is not continuous. Let's look at 3. At 3, we can see that there's a closed dot here. So it means actually there's a corresponding y value when x is 3. And again, but now, the limit from the left and the limit from the right, they are not the same. I hope you can see that. Here, the limit goes to the corresponding this negative y value, but here it goes to that positive y value. So the limit from the left and the limit from the right are not the same, though the function is defined at 3. So because the limit does not exist, then the function is not continuous. And when x is equal to 5, the limit from the left and the limit from the right, they exist, they go to this certain y value, but the corresponding y value when x is 5 is this dot here. So because we have an open dot here, and that closed dot is not the same thing as the limit. I mean, when the limit coming from the left and the limit comes from right, it doesn't go to this closed dot. So in that case, we say that the function is discontinuous. I'm going to skip these notes here. If you did not understand what I said, then you can just go through these notes. They will explain exactly what I just said. Let's go to the other example. We have 3 functions here, and we are asked where these functions are discontinuous. Remember, we said for a function to be continuous, the function needs to be defined at that point. The limit should exist at that point, meaning from the limit from the left and the limit from the right should be the same. And the third point should be that the limit should be the same thing as f of a. So basically, that's what we need to check, that is there any point on any of these functions whereby we have a discontinuity. Looking at the first function, obviously x cannot be 2, because when x is 2, you have 2 minus 2, which is 0, which is undefined. So it means actually you have a discontinuity. It does not mean the limit does not exist. Don't get that right. Don't get that wrong. We just said that we have a discontinuous because f of 2 is not defined on this function. But when x is approaching 2, the limit might exist, but x is equal to 2. I mean, f of 2 is not defined. So we say the function is discontinuous at 2. Looking at the number b, the function number b, this is a hyperbola. It's a function that looks like this. Remember that here we have 1 over x squared, so x can be negative, but because this is same thing as y is equals to, y cannot be negative, so it's a function that looks something like that. So, and they say, obviously, x cannot be 0 because we cannot have 0 in the denominator. And they say when x is 0, the function is 1. So meaning actually when y is equals to 1, this is the part. But the limit from the left and the limit from the right, both of them are going to infinity and they're not equals to 1. So that's why we have this condition on number B. And looking at number C actually is, because remember we said the limit this function is not continuous at, or is not defined at 2. So number C, actually, they took number A and they defined what y is 1 when x is equals to 2. But does it mean that the function is continuous at that point? Think about it. Yes, is defined, but when you evaluate the limit when x is equals to this function, it does not equals to 1. And because now the limit does not the same as the function, and it does not equals to y, the f of a at that point, or f of 2 in this case, it means actually the function does not exist. And like I said, number C, we found the y, the corresponding y when x is equals to 2, but now that y is 1, but evaluating the limit, you can factorize the numerator so that you can cancel out the x minus 2, we get x plus 1. Now we have a straight line, we can do a direct substitution, or a polynomial can do a direct substitution, but the limit now goes to 3. And you can see that the limit does not correspond to the f of 2. F of 2 is 1, or the corresponding y value when x is 2 is 1, and it's not equals to the limit. So for that, we say that the limit, the function is not continuous at 2. Yeah. So basically, these are the 3 functions that we've been looking at. So here you can see the first one, we had open dot at 2. This was the function was discontinuous. Number B, the limit from the left and the limit from the right is not equals to f of 0 here. And the third one, we can see that the limit from the left and the limit from the right also does not the same as the dot here. So that's why the limit does not exist here. Please note that for number A and number C, though this kind of discontinuity is called removable, and it's called removable because you can factorize and cancel out and end up having a polynomial that you can just do a direct substitution, just like here. You see that we factorized, we canceled x minus 2. X minus 2, then we are able to substitute x equals to 2. So such continuity is said to be discontinuous, removable discontinuity. Then looking at number A, because the function is going to infinity at that point, we say that this is an infinite discontinuity for this one. Let's continue. And again, remember that we spoke about the limit from the left, the limit from the right. Even for discontinuity, the function can be continuous from the right or continuous from the left. But generally, the function is not continuous at that point. But looking at that point from the left, then we say the limit exists. I think it's pretty much obvious looking at the definition. So if the limit from the left is the same thing as the function at that particular point, then we say that the function is continuous from the left or from the right. So in this case, because remember we're coming from the right or from the positive side, so we say that or for values that are greater than a, so we say that the function is continuous from the right at that particular point. And for this one, we say the function is continuous from the left at this particular point A. We can look at the previous examples that we just did. Here at 3, you can see that coming from the left and f of 3, the limit is the same. So it means the function is continuous from the left at 3. But at 3, we say the function is discontinuous because the limit from the left and the limit from the right are not the same. So there's just an example. So generally, we say that the function is continuous, or the function is continuous on an interval, meaning each and every point in that interval, the limit exists, and the limit is the same thing as the function is defined at that point, and the limit and the function being defined at that point, it is the same. So basically, if you have an interval whereby all those 3 conditions are met at every point, or every point in this interval, then we say that the function is continuous on that interval. And same thing with the limit from the left and limit from the right, we can say the function is continuous from the left on an interval, right? Meaning f of b might not be defined, but each and every other value might be continuous or might be defined. So we say the function is continuous everywhere else in the interval. So the function in that case, because it's not defined at the end point, so we say it's continuous from the left right? And same thing here, we say the function is continuous from the right because it is continuous at the right endpoint, and when it's defined on the interval and even in the bounds of the interval, then we say the function is continuous everywhere in that interval. Let's look at an example here. So we are asked to find actually to show that the function is continuous on this closed interval here. And I hope you can see that this is a circle. This function is a circle, but remember that for you to be able to say that something is a function, you need to use the vertical line test. So because the vertical, if it's a full circle, then the vertical line test will fail. Remember, a circle is something of that sort. So using the vertical line test, it will intercept the function twice. So it's not a function. So for that, we need to limit the function. We need to limit the curve so that we either use the upper half or the lower half of the function or of the curve so that it becomes a function. Because in that case, then the vertical line test will just intercept the function just once, depending whether we just use, regardless whether we use just the upper half or just the lower half. So this is a circle that is being moved 1 unit up, if I'm not mistaken. For you to prove, you can take the square root on the other side. So basically on the left-hand side, you will have the square root 1 minus x squared. Then on the right-hand side, remember this is same thing as y. So you can take y on the other side, you end up having 1 minus y. Then from there, you can square both sides. You can square both sides. But again, remember that now squaring both sides, the square and the square root will cancel out. You're just left with 1 minus x squared. Then from here, you're going to multiply out. Then from there, you collect the terms, do complete the square. You end up having a circle that is being shifted, I think 1 unit up, if I'm not mistaken. Yeah, and I think it will also be a function of radius 1, if I'm not mistaken again. Okay, but otherwise, remember right now, I'm just focusing on continuity. I'm not focusing on seeing that this function is a circle. So that can be your homework. And because, and it can be your homework, whether it's the upper half of the circle or the lower half of the circle. So remember, this is our interval. So we can see that actually this function, if you take any value that is between -1 and 1, because remember x squared is always positive, and we need the number inside the root to be positive, right? So it means that that number will always be less than 1, because this is 1 minus. So that number will always be less than 1. So it means 1 minus that number that is positive, that is being squared, it will still be a positive, so we can have positive number. So in that case, we know that our function is going to be continuous in this interval, meaning any a that we choose that is between -1 and 1, it should work. But now we need now to check the limit if it will be the same thing as f of a. Remember that we're excluding x is equals to -1 and when x is equals to 1. So we're excluding the endpoints. We just want to see what happens between. So now taking the limit when x is approaching of this function. Now remember from the limit laws, we can take the limit to be inside the root, and we have a polynomial inside the square root. So we can do the distributive. So basically we have, you're looking at this is a polynomial. 1 minus x squared is a polynomial. So remember when you did the limit laws, we said when you have a polynomial, you can do the direct substitution. So basically you can just do a direct substitution here so that you have 1 minus a squared. And remember that we said a is between -1 and 1. So in that case, it means actually the root is still defined. So we can, so meaning the limit is the same thing as f of a. So the function, we can say that it's continuous at a if a is in between -1 and 1. And again, looking at the limit from the left, otherwise the function here is the lower half of the circle. When approaching -1 coming from the right, we go y goes to 1, and that is when you substitute 1 for this function, because remember when you substitute 1, you have 1 minus 1, which is 0, square root of 0 is 0, so y is equals to 1. So coming from the right, we get the same, we get y is 1, is something as the limit. Coming from the left, we see that the function also goes to 1. So we can say that the function is defined at 1, because when you substitute 1, y also is also 1. And again, the limit from the left, the limit from the right are the same when x is approaching or everywhere from -1 until 1. So in that case, you can conclude that the function is continuous. The function is continuous on the closed interval. Again, for these functions that are continuous, so these are called the properties of a function. We have what's called the composite function, the product of function, the difference of function, quotient of function, and all these. So basically, I've skipped this part, but otherwise, most universities, this is where they have to start when they introduce functions. So basically, it means actually we can apply these properties only for continuous functions. Otherwise, you'll get error. And again, let's take another theorem here. It says any polynomial. So any polynomial doing a straight line, your cubic, your parabola, all those functions, the polynomial functions, they are continuous everywhere. That is because we don't have any open dot anywhere in when you have a polynomial. And again, for rational functions, remember, rational function is when you have a polynomial over a polynomial. Those ones that have division sign. So you have a function over a function. So that is called a rational function. But those functions, they need to be polynomials. If you have a square root over exponential function, then that is not a rational function. That is just the quotient function. So rational function is continuous everywhere as long as it's defined. Remember, it's defined, meaning you have to give the domain. And for the rational function, the condition is always that on the denominator, you cannot have 0. So because where you have a denominator of 0, you exclude all those points. So it means everywhere else, those points will be in the domain. So such function, they are continuous everywhere on that domain. We have a rational function here. So now we are asked to evaluate the limit, use the theorems in this example to find actually the limit of this point. So for us to be able to evaluate or to use those limit laws, like we did in the example, these functions, they need to be continuous. So in the numerator, you have a polynomial, in the denominator, you have a polynomial. So when you have a polynomial, we know that the polynomial is continuous everywhere, but otherwise this is a rational function. So the function is not defined when on the denominator when you have 0, and you can only have 0 when x is equals to 5/3. So it means actually this function is rational and the domain is everywhere else except when x is equals to 5/3. So for that, for us to be able to evaluate the limit when x approaches -2, it means actually we can do the direct substitution because x is not approaching 5/3. So because now a function is, the domain is everywhere, we can be able to substitute -2 directly. So basically we can evaluate the limit. So the limit is just something as doing a direct substitution. So doing a direct substitution, it means everywhere you see x, you substitute -2. So you get -1/11. So it means actually the limit of this rational function should be -1/11. Mind you, actually, we said we just used these theorems that we just did here, the one that we just visited here. Okay. Now let's go to the sine function and the cosine function. Remember, people, like I said, when we started these, we did not start first with introducing the functions, talking about the domains, talking about the inverse functions. But otherwise, because I want to give you some work for you to do, or some things for you maybe to look upon, I've included some examples here, which somehow actually are out of scope, or maybe I don't expect you to be able to follow directly, but otherwise for you to be able to follow, you're going to need to do a little investigation a bit, and trust me, that will help you a lot. So, so basically, if you look at the sine function, remember the sine function, wait. So the sine function, remember, the function does it's continuous everywhere. There's no point whereby the function is undefined. We do not have any open dot everywhere, both for sine and both for cos, right? So these functions, they are continuous everywhere, even at 0. They are continuous. But because remember that the function of 10 is sine over cos, then the function is continuous everywhere except when cos is 0. And cos is going to be 0 when pi theta is pi over 2. And again, I know that you guys do not know what these are. These are called the, just like normally I know that from high school, most of you, when calculating angles, you use degrees. And on your calculator, you'll see that actually there's radians, there's degrees. So basically this is calculating degrees using radians. So basically pi over pi, let me just give you a short. So pi is the same thing, is equals to 180 degrees. So it means pi over 2 is 180 over 2, which is 90 degrees. So basically it means on a Cartesian plane, because normally we have 90 degrees. We have 90 degrees here. So in radian measure, it means actually here on the y-axis, this is just pi over 2. So basically we have 0, pi over 2. You have pi here, which is 180. So here it's 3 pi over 2 because this is 270. Remember, pi 180 over 2 is 90 times 3 is 270. So basically here, this 270 is 3 pi, 3 pi over 2, and the 360, or the normal, the one that we call 360 in radian measure, we say that it's 2 pi. So basically all these, so this is, again, this is 270. This is, see, 90 times 5, it's 450. So this is 450 degrees. So this is the measure that we use in university to calculate angles. So basically pi over 2, remember, like I said, the function of cos at 90 is 0, at negative 90 is 0, and it just keep on continuing like that. So all these points whereby the function crosses the x-intercept, that's when cos is 0, because the corresponding y value for that x value is 0. So those are the points where cos is 0, and these are the points when cos is 0, and in that case, it means actually 10 is not defined at those points, and it means actually 10 has asymptotes at those particular points. Vertical asymptotes. Remember I told you that there's different types of asymptotes, but now I'm talking about vertical asymptote because the function is not defined at that particular point. You can see that at 90 or at pi over 2 or at 270 or at negative 90 and negative 270, all those functions, that's when you have the asymptote. I believe you already know the shape of the 10 function, and that's how it gets to look like. And those discontinuities at those points are called the types of the infinite discontinuities. Yeah. So, and again, talking about inverse functions, and again, please go and investigate on inverse function, what happens about their domains and the range. Go and investigate on the one-to-one functions, what happens about the domain and what happens about their range, which functions actually do have inverse functions, which functions do not have inverse functions. And actually, if it is an inverse function, what is the type of that inverse function? And again, the interpretation of an inverse function is when you reflect the function along the y is equals to x. So suppose this is our Cartesian plane. So suppose actually you have x here and you have y here, right? Let's say you have a function that looks something like that. The y is equals to x line, it crosses the x, sorry, remember that it passes through the origin. So basically, if you reflect this line, it means actually this dot, it will come here. I think it has to, the function has to look something like this. So you can see that this function has been reflected. So that's what an inverse function means. It means reflecting along the y is equals to x line. Remember this, the one going through the origin, this is y is equals to x. Okay, so if the function has no break, right? So it means actually break meaning it has no asymptotes. It has no asymptotes. It's defined everywhere. It means actually its inverse will also be defined everywhere. And talking about trigonometric functions, they are continuous, right? And it means actually, but you need to be careful about these trigonometric functions because they are continuous everywhere, but where they had asymptotes, it means actually the inverse could actually behave otherwise. So I'm going to leave that for you. Again, this part of talking about functions, talking about the inverses, talking about the domain and the range and the one-to-one is a big topic because it leads to that point of talking about root functions, talking about the composite functions. Where did functions result? You know, when you move around the transformation of functions. So that part of actually the functions, it's a very big topic. So I'm talking about it shortly here, but otherwise it's a very big topic. And again, from your metric, logs, I think they've been discontinued. You guys are not doing logs anymore, but you come to university, logs are being introduced back, and you get now to draw a function and not only do properties or just manipulating or playing around with log properties, but actually you get to draw the function and gets to know its domain. And here, because we're talking about continuity, the domain of the log function, it's 0 to infinity, and it means actually it's continuous on 0 to infinity because it does not have any asymptotes from 0 to infinity. So all these functions, they are continuous everywhere at their domains. Exponential, so basically we're talking polynomials, we're talking rational functions, we're talking root functions, we're talking trigonometric functions, logarithmic functions, exponential functions. By the way, these are inverse of one another, the exponential functions and the logarithmic functions, but I'm going to leave that to you. And same thing as the inverse of these trig functions. And again, the root functions actually, maybe let me stop ruining things, but otherwise the root functions are the inverse of these polynomials. Yeah, for example, look at this function. And the question is, you can see here, you have a ln function. Again, I included this here to just pop up your eye so that you can be interested, so you can go investigate. A ln function is a function of, it's a log with a base e. Base e. So basically a function ln x. Ln x is the same thing as the log function, but with a special base or log e. And again, this e is a constant, just like we have pi. Remember, pi is a constant, so e is also a constant, and it's I think it's approximately 2.71 something. It's a rational number as well, so 2.71 something. And again, this number e, it has lots of applications, many applications. So that's why it's sort of special. So looking at these functions, remember we said logs, continuity of logs, we said logs are continuous from 0 to infinity. Obviously, you need to read a lot so that you can be able to understand. Here we have inverse 10 functions. Maybe I shouldn't do this example, but otherwise I include this example for you to be able to go and look at this function. So the function of log is a function that it looks something like this. It does not touch the y-intercept. So it's continuous for all values that are greater than 0. The function of 10 is continuous everywhere. Remember 10, remember the function of 10, the function of 10, just to walk you through, it gets to look something like this. It has a asymptote at 90 at negative 90. So remember, if you get to reflect it along the y is equals to x line, actually the 10 function, it gets to look something like this. Remember, y becomes x and x becomes y, and it will have horizontal asymptote. at 90 and then at negative 90. So the function gets to look like this. So remember, it will just continue going straight and straight, just doesn't get to cross, it just doesn't get to cross this dotted line. So it means actually the function is continuous everywhere. So the inverse of 10 function. And obviously the parabola, you can see that we have a polynomial, which is a parabola in the denominator. It is continuous everywhere, but we don't want the denominator to be 0. So, and that will only be 0 when x is plus or negative 1. So it means actually, because we have continuity is continuous everywhere for positive values, continuous everywhere, and taking this, so combining all these domains, we get to see that actually our function is continuous. We have 0 to infinity because this, the ln function or the log function side, actually we only need the positive values of x. So that's how we got 0 to infinity, but again, we excluded -1, so we need to include that one. So basically the numerator, it means actually this is the domain of the numerator, but for the denominator, because remember we said we only want the positive, so we go from 0 to 1 and from 1 to infinity. So it means this function f of x is continuous from 0 to 1 and from 1 to infinity. Maybe let's look at the following example. Remember, we said pi is the same thing as 180. So we have a function here, we have a sine function over a cos function, and we want to investigate, to evaluate the limit when x is approaching infinity. So looking at the function of sine, the function is continuous everywhere. The function of cos, the function does not have any open dot anywhere, so the function does not have an asymptote, it's continuous everywhere. But now, remember we said we don't want the denominator to be 0. So normally the function of cos, it goes something like that. So it goes as high as 1 and it goes as low as -1. But the function of 2 plus cos x, remember it's a function that has been shifted up. So instead of starting at 1, it will start at 3, because you remember you have to move it 2 units up. So if maybe 2 is here and 3 it's somewhere here, so the function will move here, and the lowest point was -1. So -1 plus 3, it gives us 2. So it makes actually, it gives us -3, 2 minus 1, it's 1. So it means actually our function will go as high as 1 and as low as -1. So it means actually we never get a y value that is 0, or it does not touch the x-axis. So it means our denominator, it's never 0. So if our denominator is never 0, it means actually our function is defined everywhere. And I hope that part is clear. So because it's continuous everywhere, to evaluate the limit, we can just use the direct substitution. So when you substitute x for pi, remember I said pi is equal to same thing as 180. So sine 180, remember the function of sine, it goes start from 0, go to 90 degrees, then come back. So basically means this part, the highest point is a pi over 2, and this part on the x-axis is pi. So that's why we get 0 here. And for the function of cos, remember the function of cos, it starts at 0 at pi over 2. That's when it's 90, it's equals to 0 because it's on the x-axis. So negative pi, it goes to its lowest point, which is -1. So that's why here we have 2 plus -1. So because of 0 in the numerator, we just have 0. So our limit is 0, but the function is continuous at x is equals to pi. Okay, remember earlier I spoke about functions. I said the section of functions is a very big function. It's a very big function. So there's a theory called composite functions. So composite function is just like you know substitution. You know, when you for example, f of 2, it means actually wherever you see x, if maybe you were given f of x, sorry for my bad handwriting. Say, suppose you are given f of x and you ask to find f of 2. It means wherever you see x, you substitute 2. So composite function means actually, for example, say, suppose you're given f of x and you're given g of x. So basically composite function, it means actually wherever you see x in f, you can substitute the entire g of x. So Maybe for you, if you have a deep understanding, and actually even same thing for G, you can have G of f of x. So it means actually in the function of G, whenever you see x, you substitute f of x as it is. And again, please note that these are not the same. F of G of x and G of f of x are not the same. So the theory of continuity, it works even for continuous, for composite function. So if function is continuous at B, right, and the limit of G of x is equals to B, so basically the limit of this, remember f is continuous at B, it means actually, and the limit of f, so basically you can take the limit inside. That's what the theorem is trying to say. So you can distribute the limit because you want to get to x. So you can take the limit to be inside. Yeah, so that's what it says. We have an inverse sine function here, and we have root function here. So as I said, I include these examples because I thought they are a bit harder than the usual functions that we normally just use here for explanation. So again, remember the sine function, right? Remember the sine function, it starts at 0, at 90 it's 1, then come back. So it means actually finding the inverse, right? You remember the inverse, it means actually, so maybe I shouldn't go too deep into this, but otherwise go investigate on the inverse of functions, right? Go investigate on the inverse, because that's this function it is a continuous function, but go investigate if it has asymptotes. Is there any point whereby this function has asymptotes, or actually, because the function of sine, it gets to look like this and all that. First of all, can you find the inverse? Or for you to find the inverse, is there something that you should do to this function? Because otherwise, remember the y is equals to x line, it passes through the origin like this. So if you reflect this function along this line, how would it look like? And if it gets to look like that, I think by just the look of things, remember we said this is y is equals to x. So whatever the way y was behaving, x gets to behave that way. So because the function was looping around the x axis, so the function will get to loop around the y axis like that. But then when it's like this, when you use the vertical line test, it cuts the graph multiple of times. So it means actually the inverse of sine function, it's not a function. But for you to make it a function, it means actually you need to limit its domain. So remember, if, for example, the function gets to look something like that. So suppose maybe you want it to be 1-to-1. And again, those are the conditions for the function to have an inverse. So you only want this part from pi over 2. Remember, pi over 2 is 90. So you have 180 here, which is pi, and this means this part is 3 pi. 3 pi over 2. Yeah, 3 pi over 2. So suppose you take this part and you reflect it. So that's when the inverse can exist. So basically you have the sine inverse, but it's not of theta. Our theta is 1 minus root x, 1 minus x. So remember, even inside our angle here, there's a certain point or a certain values that it can be, it's not, for example, we cannot have x to be negative. And we cannot have the denominator to be 0, so x cannot be 1. But otherwise, for you to be able to evaluate this, we can use this theorem of composite functions. So basically, like we said, the limit can be distributed to be inside the function. So we can skip the, okay, by the way, arc sine is the same thing as sine inverse. It does not mean that the function has changed. So sometimes some textbook, they call it arc sine. Some textbook, they just leave it at sine to the power -1. Others, they just call it sine negative as arc sine to avoid that, because sine can have exponents. So that sine -1, it does not mean that, sine to the power -1, this we don't expect, mistake this to be an exponent, but to understand that it's a notation, not an exponent. So that's why some textbooks, they rather prefer to just call it arc sine. Same thing even for tan, for sec, for cosec, yeah, all those functions that we get to be called arc, sec, and all that. So basically, you can distribute the limit inside. So obviously here, we said we are approaching 1. So obviously, looking at the numerator here, we can evaluate the root of x approaching 1. Okay, I'm not sure. Wait. Oh, or what we had to do, we had to rationalize the numerator. So by doing, I mean, the denominator to remove x approaching 1. So we multiplied by x plus 1, both in numerator and in the denominator. Or actually, what we did, we factorized. Remember that root x. Remember that root x times root x. Multiplying. Oh, my handwriting is very bad. Let me see if I can use a different pen. Okay, basically what I'm saying is that when you take root x and you multiply it with root x, that's when you get to, you get x. So basically means on the numerator here, we can factorize 1 minus x to be 1 minus root x times 1 plus root x, difference of 2 squares. I hope that part is clear. So 1 minus root x cancels with the 1 minus root x. You're left with 1 over, remember, removable discontinuity. That is what we're doing here. So we canceled out here, and in the numerator, we can substitute. We can take the limit inside the square root. So square root of 1 is 1. So that's why we have 2 in the denominator. And sine inverse of 1 over 2, it's pi over 2. And again, for you to understand where do we take pi over 2, remember I said, like I said, pi over 2, it means 90 degrees. So sine inverse, remember that normally you substitute x being the degree and y becoming just a constant between 1 and 2. But for the inverse, it means actually y is the one that gets to take the angles, meaning the degrees or the radians, the angles, and x is the one that gets to take the values between 0 and 1. Like you see here, our x input was just 0.5. So that's what I meant when I said go investigate on these sine functions. So let me just erase this so that we can continue. Okay. So this is the notation for composite function. So it said that if G is a continuous function and F is also a continuous function at G of A, then these rules can apply. But otherwise, please do not stress much about this composite function. If you haven't, just go and investigate on this composite function. But otherwise, I included this part so that you can see that actually there's, we're not only focusing on limits so that you don't get bored. We have another function here, our sine function, but instead of just sine theta, our theta is x squared. So actually, this is also a composite function. Because if you think of h as f of g, whereby the function inside, remember theta, our g is just x squared, which is a parabola. And so we substituted a parabola inside a sine function. So basically we have f of g. So as I said, this sine x squared is a composite function. So now g, which is a parabola, is a polynomial and is continuous everywhere. Here we have a sine function, it's continuous everywhere. So it means actually this function h is continuous everywhere. We're just trying to give an example of the results that we have here. So this is just an example to show that actually for you to know where is the function continuous, you can look at its sub to see it as a composite function and look at its these pieces of the function that makes the function to evaluate its continuity. Now, looking here, again, we have a composite function. Here we have a ln function, which is, remember I said, it's a log with special base e. And again, we substituted 1 plus cos. So 1 plus cos is a function that has been shifted. It's shifting the cos function upwards. So we substituted the function that has been shifted inside the ln function. So it's very important for you to know these things. Otherwise, when you look at this and this function of ln 1 plus cos, and you see it as a because remember we want to know where is this function continuous, and for us to know where exactly is it continuous, we substituted g and we substituted, we see the capital F, meaning the function as the composite of small f, I mean g inside the small f, so we see g as 1 plus cos x, and this small f as the ln function. So from that, we know that the ln function, like I said, if you remember, the ln function, the log function, is a function that looks like that. This does not touch the, it's an exponential function that is tilted, that is being, remember that actually, yeah, our normal exponential function is being rotated along the y equals to x. So it gives the log function. So this function, remember the exponential function, its range, it's from 0 to infinity, right? Sorry, it's from 0 to infinity. That's its range. So the range for the exponential function is the domain for its inverse. So the domain here, x goes from 0 to infinity. As you can see that it does not touch the x equals to 0, does not touch the y-axis, just like the way the exponential function does not touch the x-axis. So basically, this function of this ln function is continuous from 0 to infinity. And looking at the function of cos, it's supposed to be continuous. It is continuous everywhere, but otherwise we have to consider that actually we need it to be positive. But looking at the function of cos, remember that the function of cos, remember the function of cos starts from 1 going to -1. So there is a point whereby it goes below the x-axis, so it becomes negative. But because this is 1 plus, it means actually it goes, we shift it up. So instead of starting at 1, it will rather start at 2. And instead of the lowest point being at -1, it will rather be at 0. So it will go from 2 going to, going to 0, then going up. But then it means the input, remember that we said this 1 plus cos is an input to the ln function. And we said ln function does not take 0. So it means actually we need to exclude where 1 plus cos is 0, meaning this particular point, its lowest point. Remember, this is at 90, this is 180. So it means at 180, we have to exclude those points. So that means actually we have discontinuity at those when x is equal to pi, or when cos is equal to 1 plus cos is equal to 0. So basically we have vertical asymptotes when when cos x is equals to -1, or when x is equals to pi, or the multiples of pi. Yeah, so it means actually the function is continuous everywhere on R except for the multiples of pi. Yeah, so basically this is how the function will get to look like. Looks like a frog's movement, or the path of the frog, if ever it moves in this way. So basically we have, as you can see, it means the asymptotes will be here. So the function is not discontinuous. I mean, the function is discontinuous on these multiples of pi. Okay, lastly, the very important theorem called the intermediate value theorem. This theorem is very, very important, especially when you want to know whether your function has a solution, or you want to know it has a unique solution or it has many solutions. So this function intermediate value theorem, we get to use it. And remember that the intermediate value theorem, there's one for integrals, so there's a number of them, but this one is just called the intermediate value theorem. So do not confuse it with other theorems. So it says that suppose you have this function that is continuous, and is continuous on the closed interval. And now, if this function is continuous in this interval, let n, right, be any number between f of a and f of b. Remember that the function is defined at a and the function is defined at b, because we said it's continuous, right? So there's some number, remember this number, remember f of a and f of b, those are the y values. Let's say a is here, and let's say b is somewhere here. So let's say at this particular point, we have our f of a here, Sorry, my handwriting is very bad. Okay, let me see if I can use the other pen. So, no, wait. I want to use, yeah. So suppose here we have B. So obviously this particular point, our f of A is going to be somewhere here, right? And our f of B is going to be somewhere here. That's the value that, so basically I'm talking about a function that looks something like that. So it is defined at that point. So for these y values, we say that there's some number n that is between f of A. So maybe let's say n is somewhere here, right? So y is equals to n is just the horizontal line going like that, right? So he says that this number n, f of A is not equals to b, it means actually they are not the same. They are not the same. For example, when you look at this parabola, if A is here and B is here, it means actually f of A and f of B will be the same. So that's what we mean. In this case, we don't want them to be the same. We're saying that there exists some number C between A and B. Let me erase this part so that you don't get confused. I was just explaining the part of A, f of A and f of B being the same, or in what situation they get to be the same. So we said, in this case, we said we don't want them to be the same. So if they're not the same, f of A is different from f of B, and we're saying that there's some number n, some horizontal line, and we're saying that actually this horizontal line, it becomes some f, or it becomes some corresponding y for some number C, and this number C is in between A and B. Let me repeat this again. You have this continuous function. It means actually it does not have discontinuity, or it does not have those any vertical asymptotes, or it does not have those open circles anyway. So, and we have your f of A and f of B is defined. So, and f of A and f of B are not the same. So we say that actually there's some number there exists, or we can say that actually let n be some number n, and this number, it's this y value is between f of A and f of B. And this y value, for the fact that f of A and f of B are not the same, and we have some number between their corresponding y values, it means actually that particular y value, this n, it is a corresponding x value, and that x value will be between A and B, and that number we call it, we say that it's C. So that's why we say f of C is that number n. So that's what the intermediate value theorem says. So I'm going to erase all this so that we can take an example, see actually when do we get to use this theorem. Like I said, see we have A, here's our f of A, corresponding f of A, we have B, we have our corresponding f of B. So you can see in this case, f of A is greater than f of B, and they are not equal. So we say that these corresponding y values, f of B and f of A, we have some y value here, we call it n. There's this number, if we have some, let n be some number in between. So in this case, it means actually that n, it will have some corresponding x value, we call it C, such that this C is in between A and B. So any number that is in between f of A and f of B, as long as f is continuous, then it's going to have its corresponding x value. That's what the intermediate value mean. So let's take, for an example, we want to use the intermediate value theorem into locating the roots of equation in this example. Remember, root, it's when you search when you solve for x, is when you have your f of x, is when your y is 0. So basically you have your f of x is equals to 0. In other words, in graphical terms, it means actually on the x-axis. You're looking for points in the x-axis because that is the point when y, remember f of x is y, so we want the point where our y is equals to, my handwriting is very horrible. So we want the parts where our y is equals to 0. So basically, there is examples asking us to show that there's a root, or we can find the solution. And that solution is going to be in between 1 and 2. So we're supposed to use the intermediate value theorem to show that there's a root. But otherwise, if we let this left-hand side become our f of x, right? And remember that we've been given our interval between our interval here, we said that it's between 1 and 2. So if we substitute 1, because this is a polynomial, so it's continuous everywhere. We know that part. So it's a polynomial, so it's continuous. Remember, that's one of the very much important need for this theorem to work. The function should be continuous. So this function, given that we already know that it's continuous, it means we can now use the intermediate value theorem. So what I'm trying to say is that before you use the intermediate value theorem, you have to show that the function is continuous. So you need to show that actually you can use the theorem. So if you substitute x to be 1, we get negative, the corresponding y value is negative. If you substitute x to be 2, the corresponding y value is equal to 12. So we have a negative value and a positive value. So in other words, we don't know how this polynomial is a cubic. Let's say it gets to look something like that. So when x is 1, we get this negative value. But otherwise, because the function is going up, when x is 2, remember this, for x, we got a negative y value. And for x is 2, we got corresponding y value. It means actually in between 1 and 2, there is some x value such that its corresponding y value is 0. Because it means for y needs to go from -1 to 12. So it means actually there's a point whereby y needs to be 0. So you say when that part when y is 0, there should be a point. We don't know what that point is, but otherwise we are saying that since, well, c is between 1 and 2, it means actually f of c will have to be between f of 1 and f of 2, and such that this f of c is 0. So this f of c is n in terms of when you want to use the theorem. The theorem was saying that let n be some number between f of a and f of b. So in this case, our n is 0, and and this n is in between f of 1 and f of 2. And this is how the function gets to look like. You can see that when x is 1, you get -1. And when x is 2, you get positive y value, which is 12. So we say that in between 1 and 2, there's some number here, which we call c, such that number, okay, sorry. So that number here is c, such that f of c is 0, meaning y at c is 0. So that's meaning that is our x-intercept, and our x-intercept, those are our roots. So that will be all for today. And I think we've covered a lot so far. In our next class, we'll be tackling algebra. So we'll be tackling matrices, we'll tackling simultaneous equation. In other words, the simultaneous equations, but inversity. Obviously, in high school, you guys did simultaneous equations in terms of 2 equations or 3 equations, but in varsity, you can do 4 or so many. So otherwise, what we'll be doing on the next lesson, it will be doing the part that is called linear algebra. And that linear algebra, most of you will be the first time using such. So pay attention and come to class when you're very much fresh. And that will be all for today until we meet again.